I'm Giuseppe Macoretta. I'm a researcher in metallurgy at the University of Pisa, and today I'll present you an ongoing activity that we are carrying out together with our research group and Eni, that is an Italian oil and gas company. We'll deal with the effect of gaseous hydrogen on the static mechanical properties of commercial pipeline and casing steels. So we'll deal with standard commercial steels that are already used, and we want to assess the effect of gaseous hydrogen, and so the application linked to hydrogen transport and hydrogen storage. We'll see the material and the method that we used, some metallographic analysis to understand the features of the material, the results of the slow strain rate tensile curve tensile test that we carried out, and so cures, and we'll see comparative fractographic analysis that allow us to understand the effect of hydrogen on the material and so the enrichment of the material. We work with hollow specimen. It's an hollow specimen with an internal hole produced by drilling, and in this case, reaming, with a diameter of 3 millimeters. We introduce in the specimen gaseous hydrogen at a pressure of 10 megapascal, but we can reach even 20 megapascal. We use hydrogen with high purity, with research grade purity. The specimen presents a true hole because it's used for purging with hydrogen. So we have a pressure cycle before starting the test. At least 5 times we pressure the specimen. We release the pressure at least at 3 megapascal. And we pressure the specimen again, so we don't reach the atmospheric pressure to avoid the entrance of air. And the specimen is pressurized at least 10 hours before testing because we want to be sure that we have no gas leakages before the test. And so we don't want that something can affect the test because the test is very slow. This is the specimen. This slow strain rate tensile test is carried out in displacement control with a displacement of 0.1 micron per minute, per second, let's say. And so we obtain an effective average strain rate of 1 at 10 at -6 hertz. So it's a very slow tensile test. Here you can see the test configuration. In the middle of the picture, you can see the hollow specimen with an extensometer to monitor the deformation of the central portion of the specimen. You can see the clamping ring that is simply a fixture that applies the load to the specimen, decoupling the load from the pressure fixture. We have the gas connection, and on the gas connection, a pressure gauge to monitor the pressure, the effective pressure in the specimen during the test. Materials, we deal with X60 pipeline steel in the seamless configuration, so pipes produced via seamless process, and thermomechanically controlled processes materials, so a material produced by welding, by bending and welding sheet steel, and casing steel T95 and P110. All the specimens were extracted from the pipe along the longitudinal direction, so with the longitudinal specimen direction aligned with the pipeline longitudinal direction. About the chemical composition, we are dealing with low carbon steels, in particular for the X60, but in all cases, we have a carbon content lower than 0.3, more or less. Let's start with the assessment of the surface integrity of the hull. The hull, as I said before, were produced by drilling and reaming. So we carried out some surface roughness measurement on the internal hull of the specimen, and the results are most in line with what we can expect from a reaming process. So we have an average roughness value of 0.3 microns. That is in line with the reaming process. If we also go to assess directly on the microstructure the effect of plastic deformation produced by the drilling and reaming process on the material, we can see that the drilling process affected thickness of about 25 to 20 microns, both in case of the X60 TLCP or X60 quench tempered material. You can see with the difference, it's more evident in the first one because of the more ferrite grains. Let's start with pipeline steels. Let's start with the microstructure of the material. Both materials are defect-free. It's a standard defect-free material used in the hydrogen in the oil and gas industry. If we take a look about the microstructure for the CC quench and tempered material, we can see the standard acicular ferrite that is typical from the quenching process of the solo carbon steel, while in the TMCP material that was produced by submerged arc welding and then an homogenization process, we can see more ferrite grains with some ferrite aisle. If we go to see the results of the loss and rate tensile test, we can see that the effect of hydrogen, here we see the typical curves that we repeated at least 2 times per each condition of the test, and I show here the typical curve that you observed, but the dispersion of the data is the scatter of the data is very low. We can see that the effect of hydrogen for both the material it's something that affects only the plastic portion of the curve. The elastic part of the curve is not affected, and the effect becomes more evident after the necking phase. Until the necking, the material is not affected by the hydrogen present inside the hole. If we go to the displacement I showed, if we go to the fracture surface to analyze the effect of the hydrogen on the material, we can see that the material without hydrogen, so the hydrogen-free material, presents a standard ductile surface with standard microvoid coalescence, some typical surface for a ductile material. While when we introduce hydrogen, at least in the first half of the specimen, starting from the whole of the specimen, we can see a transgranular fracture, and so the comparison between the two surfaces is very evident, the effect of hydrogen on this material. The same happens with the TMCP material that has a bit more ductile surface in the hydrogen-free condition, and when we have hydrogen in the material, we observe transgranular fracture. We can observe also some tears, and in proximity of tears, also some pseudo fisheye features that hints that there is some hydrogen accumulation in that places. So more deeper embrittlement effect of hydrogen, a localized embrittlement effect. If you go to see what happened with casing steel, so T95 and TP110, if we observe the microstructure, we observe that also in this case, we dealt with defect-free material with a standard tempered martensite microstructure that changes a bit between the two materials depending on the carbon content of the two materials, and hydrogen, and a bit of the treatment that the materials were subjected to. If we go to see the result of the loss rate tensile test, we see that also in this case it's even more evident because we have a reduced scatter of the data. The effect of hydrogen takes place only in the plastic portion of the curve. The elastic part of the curve is identical. Also the yield phase, even in a material like the T95 that has a discontinuous yielding phenomenon. The two curves start to differ mostly after the necking, just a bit before necking for T95, for P110 only after necking. And so the effect of hydrogen also in this material is a ductility reduction without a reduction in the material strength. If we just to see that even when we have necking, we still keep the pressure inside the specimen. So we have a pressure drop only when we reach failure. Until failure, we have a continuous section that still can keep the internal pressure. If we go to see what happens in terms of fracture surfaces, we can observe that on T95 without hydrogen, we see standard ductile surface with microvoid coalescence, a bit different from the previous one, but because of the increase in carbon content. This is the internal hole of the internal edge of the hole in the specimen, and we can see that when we introduce hydrogen, at least in the portion that is the nearest to the hole, we see a strong transgranular fracture, and so a strong change between the hydrogen-free and the hydrogen-charged material, assessing the effect of hydrogen on the material and the embrittlement effect. On the P110, the situation is even more evident. We pass from a surface with ductility features, so even in this case, microwave coalition and so on, to a surface with a strong cross-granular fracture and even some traces of intergranular fracture. This is a material that high-strength material compared to the previous one, and so the effect of hydrogen are still more evident compared to what happened in the other materials. And if we go to see what happens on the whole cross-section, we can see that we have the black one is the black portion of the image is the internal wall of the specimen. We have an hydrogen affected region that covers at least half of the thickness of the specimen. So this thickness is 2 millimeters. So the external diameter is 7 millimeters of the specimen. And here you can see that we have an hydrogen affected region where a transgranular fractures traces are evident, a transition region, and a region that is almost unaffected by hydrogen. If we go to see what happens in the region A, it was the same image that I showed you in the slide before. So a region with transgranular fracture and even some traces of intergranular. While when we go to see what happens in the B region, we see here the transgranular fracture and here the traces of the microvoid coalescence and so the ductile region. So hydrogen, when we reached fracture, affected at least half of the specimen. Then we reach a condition where the cross-section is not enough to withstand the load. And in some other portion of the specimen, hydrogen affected even a wider thickness. This is the more conservative region of the specimen where the unaffected region is more wider. Okay? You can see here in another portion of the same specimen how the hydrogen affected region reached the outer part of the specimen, and then we have only the final shear lip with some smearing traces due to the final fracture. And so, just to conclude, we observed that the hollow specimen configuration proved to be suitable for the characterization of the effect of gaseous hydrogen of pipeline and casing steels. The effect affected mostly the plastic region of the materials. So hydrogen effects take place when plastic strain is present, dislocation motion is present, and it's fundamental for this kind of materials. The effect of hydrogen intake is more or less a ductility reduction. If we want to see some numbers, more or less we have a reduction of 7 to 15% when we deal with pipeline steels. TMCP material is something that is more scattered with some defect, and so defect is greater. When we go to see what happens in terms of casing steel have high strength material compared to the previous one, and so as you use it, it's also evident in the literature. The effect of hydrogen are even greater, but we still deal with a reduction in terms of the elongation at fracture of less than 20%. Fractographic examination showed us a wide embrittled region, so the effect of gaseous hydrogen are strongly evident. And the embrittlement region is evident because we have a passing from a microvoid coalescence to a transgranular fracture for this kind of material. Thanks for the attention.